In this video, I want to cover the Fourier transform from its very basic ideas all the way through to the endpoint equations. This is really going to be useful for understanding signal image processing and also helping out in quantum mechanics as well. Right, so we've really got to understand the concept of analysis and the concept of synthesis. So I'm going to start off with a very simple motivating example. Here is a pancake. And what I'm going to do is analyze the ingredients that are inside that pancake. So if we do that, we could find out that there's a certain amount of flour, a certain amount of milk, a certain amount of salt. That would be, if you like, the analysis of the ingredients of this food. And then with knowledge of those ingredients, what we can do is synthesize or remake a pancake from knowledge of those ingredients. Another example would be in chemistry. We could consider the compound like salt. If we were to do a chemical analysis, we would find out what are the various amounts of each of the elements of the periodic table that are in that particular compound. So when it's salt, of course, we've got 1 part sodium, 1 part chlorine. And with that knowledge, hopefully with various chemical synthesis methods, we could put those two together and form salt by basically recombining those elements. And so the concept extends, I hope you'll understand, to the idea of waveforms and indeed images and signals. So on the left-hand side here, I've got a sound recording representing, basically this is a digital signal. I'm representing it here as a continuous function. So we've got some kind of amplitude as a function of time t. And we can do the same concept. We can analyze to find out what are the constituent parts of that sound recording. So typically, for sound or for signals, a very common choice is to do a Fourier analysis. And what that involves is finding out what is the amount or amplitude of particular frequencies that are present in that waveform, in that sound recording. So here I've just shown a few limited examples of different frequencies. I'll go into frequencies in more detail soon. I'm just giving examples here of various components with various amounts or various frequencies present in that sound recording by doing a Fourier analysis. And I'll give the equations and the process for doing this later on in this video. So to note here then, I'm talking about capital A to denote the amount, and I'm going to use omega to denote the frequency of a particular component. And I'll go into those in more detail as well later on. And so we can also plot that information here. So notice this is an input function here, some function f of time t. And then what we get here is a Fourier analysis of that signal, which is telling us how much, what amount A of particular frequency omega is present in that signal. So I'm showing here just a few arbitrary examples, various amplitudes for particular frequencies. And I'll go into detail later on about those amplitudes and frequencies. And then once we've got that kind of analysis, if you like, the ingredients, the constituents of what's inside that function or signal, then we can do what's called a Fourier synthesis, which will do the reverse process, which would be to take those amounts for each of the various components, sum them all together, to recombine them, to reconstruct or synthesize that original signal. Now, the synthesis process really involves a summation. So I've got an integral sign there, an elongated S for summation, to show that I'm adding together these frequency components with their various amounts in order to make that signal again. So here, the mathematical notation will be a summation over the frequencies. And we'll talk later about how I'm going to use that notation A in this summation process. To also illustrate at this point, once we've got this Fourier analysis of the constituent frequencies in some kind of signal or image, whatever is of interest, we'll be able to process quite easily these kinds of waveforms or these kinds of signals. In other words, we'll be able to do all kinds of powerful processing or modifications of that information in a way that is useful to us. And so that's what I've noted here, saying that we can process this far more easily than direct processing of the raw information or waveform. Okay, so this is a demonstration of how indeed any waveform to within reason can indeed be shown to be a synthesis of sine and cosine frequency components. So on the bottom here, I'm showing various amplitudes of various frequency components, which when summed or added together or integrated, form this black sawtooth waveform. So you can see here I've just got a limited number of frequency components, but when added together with various amplitudes, they are combining to form what looks like a very difficult waveform to create from these sinusoidal curved functions. But indeed, this illustration shows that we can do that. Here is another example. This is an example waveform, a function f of time t, showing again those constituent waveform components, those frequencies that when added together can form that red waveform. So there's the red waveform, and there is the separation into the analysis into all the different frequency components. And here we are showing the amplitude A of each frequency component omega that is present in that waveform. So this is the analysis, and that's the original function f of t. So at this point you might be thinking, well, why do this? And just to convey a key point here is that this kind of Fourier analysis, this decomposition of a signal or an image into its constituent frequency components, greatly helps with processing and analyzing those signals and images, and even can be used to modify those signals and images. So it's for analyzing them and then also modifying them. And I'll show that as a simple example in a moment. And it's all to do with the fact that these sines and cosines that we're decomposing into, that we're analyzing to find how much of each is present in the signal, these sines and cosines turn out to be very special functions that are treated in a very special way by a lot of core imaging and signal processing systems. And also, just a note here as well, that if you're interested in quantum mechanics, it's remarkable to realize that wave functions that can describe subatomic particles can also be regarded as a superposition, a summation of these sinusoidal and cosinusoidal functions, which are actually corresponding to momentum states in quantum mechanics. So this is a quick motivating slide for why we're even doing this decomposition in the first place. So here now then is an example for 2D images. I've got a grayscale 2D image on the left-hand side here, and I'm doing a Fourier analysis. This time it's a 2D image, so now the frequency components are actually two-dimensional spatial frequencies. And I'll show more of this in the coming slides. But just to give an idea, if we were to take a profile through one of these components, so also to be clear here, you need to understand that each one of these boxes should be regarded as the same size as that input image, and then that we're just adding together lots of these boxes of all of these different frequencies with various amounts in order to create that signal. So at the moment we're just analyzing it, showing that it's made up of these constituent frequencies. Again, showing a profile here, showing that one of those is indeed very analogous to those one-dimensional sines and cosines we've been seeing before. Once we've done that analysis, guess what? We can do a Fourier synthesis and use those components. Again, each one of those boxes is the same size as that input image. We can add them together to recreate the image. So at the moment, with this example, all we've done is analyze and then recombine, synthesize to remake the image. But the point is, we could do this to analyze and understand, for example, what an imaging device could be doing. So imagine we had a very poor quality camera, and so I'm depicting a poor quality camera as a system in the middle here that is effectively losing those high frequency components. And if a camera were doing that, then you can see that when we get to recombine these frequencies, those high frequency kind of edge-like details from the image are in fact missing in the output. So here we've got a nice sharp image. On the output, we've got this loss of some of those constituent frequencies that would be making up that image. And so here I'm showing how Fourier analysis can look at what is going on with an imaging device like a camera. And then if we know that information, again, this is just conveying concept. I go into more detail on these kinds of concepts in other videos, but here just the concept is that if we then had a blurred image, we could do some image processing to try and recover those missing ingredients, those constituent parts that are inside that image. So here then is the blurred image, which is missing high frequency information. What we could do is try and recover to amplify, to bring back those high frequency components such that when we rebuild the image, reconstruct it or synthesize it from those frequency components, we then get back to a sharp image again. So I hope you can see the utility of doing this frequency-based analysis and synthesis of images. So here I want to show an example, thanks to Tyler Moore, who's made this available, where we're showing a 2D image, again grayscale on the left here, showing that this indeed can be analyzed into various 2D spatial frequency components. So let me just rewind this to slow this down a bit. What you're going to see here are the various two-dimensional sinusoidal basis components, the basis functions that make up this image. And here what we're doing is slowly building an array showing the amount of each one of these 2D spatial frequencies that is present in that original grayscale image. The point being that once we've done that analysis, just like I've been showing before, we can then synthesize or rebuild that original image by knowing how much the amount A of each of the spatial frequencies we need. By knowing that, we can rebuild or reconstruct the original signal. So that's what I'm going to show here. So here we're just adding together those spatial frequencies that you saw, all of those rotating patterns that you saw corresponding to all the different sinusoidal frequencies in that image. Here with these amplitudes we can recombine them to rebuild or synthesize the original image again. So that's what I'm showing on that right hand side. Okay, let's get back to 1D because we want to start to get into some of the mathematics behind Fourier here. So here then is a 1D signal, f of t, being analyzed into its constituent frequency components with varying amounts A. So again, function A, the amount A of frequency omega present in that signal f of t. Once we've done that, we can again synthesize, rebuild that original signal. And now I want to show how we understand, in the next slide, I want to show you how we understand this amount A, amplitude A of frequency omega. So that's what I'm going to be emphasizing here. So on this axis, I'm going to be showing capital A, the amount or amplitude of a particular frequency. So I'm showing just one little frequency component here of amplitude 3. And I'm saying that's got a frequency omega of 1, which means there's one waveform fitting within a certain interval. Okay, so I'm representing the amplitude there with that height. And you can see that I could increase A, increase the amount of that particular frequency component. In other words, just increase the amplitude of that waveform. Or indeed, I could decrease the amplitude of that waveform. I could even set it equal to 0 to completely remove it. Or that's if I'm doing processing, or when I analyze a signal or an image, A would be telling me how much of that frequency component is present in the original function. Okay, so that's amplitude. The other axis I want to show here is that of frequency. Okay, this is showing how many waveforms fit within a particular interval. So you can see here that as omega is increasing, so notice A is constant here, but now I'm looking at an increase in omega, and that means we're getting more waveforms fitting within a unit interval. So here I'm just giving the example interval of 2 pi, and I'll just go back one step, and then I'm also showing the important case here of the 0 frequency, which corresponds to a flat function. That means there are effectively no periodic occurrences of the waveform within a unit interval. It's a flat function, the so-called DC offset or 0 frequency component. Now that means we can now consider all the various frequencies and all the various amounts of each frequency. So in fact this would be a continuous, a real value A, could take on any value, and depending on the kind of waveform that you're analyzing, we could either have a discrete set of frequencies if it's a periodic waveform, but generally for the Fourier transform, which is what we're interested in here, this could also, the frequency could also take on a continuous value as well, such that when we're considering any particular signal, function, or image, what we could do is say, well, okay, it's got certain amounts of each frequency that are present in the signal. And so again, I could show that with this kind of amplitude A of frequency omega tracing out this kind of waveform here, this kind of spectrum. And a spectrum, or the Fourier coefficients, are basically saying what is the amount A of particular frequency omega that is present in my signal or image of interest. Okay, so there is the example of a signal of interest being, for example, an audio waveform. So now let's take a look again at another example here. This is a square waveform, and now I'm showing, in fact, a continuous range of frequency components that, when added together, are making up that original waveform. So I'll restart that so you can see it again. There is some waveform, okay, a red waveform here, and I'm just showing that this is composed of various amplitudes. So this is the frequency axis along here. And then what we're seeing here is the amount of each of those frequencies present, such that when those frequencies are added together, they form that original waveform. So once more, just to go through that, that's the waveform f of x. And what we're seeing, you'll see the frequency components here. Just look at those sinusoidal functions there, and the amplitude of each one of them is depicted here. And that corresponds to the spectrum, the amount A of each frequency omega that is present in that original signal or function. Okay, so let's again get closer to the mathematics now. There's my f of t, my input function. I'm doing a Fourier analysis. I'll give you the equations in a moment for that. And then we've got the idea of recombining them in a synthesis to rebuild the original function. So now to get to some of the mathematics, we're saying we've got an amount A of frequency omega, so that's A of omega, and that is a scaling factor or a coefficient or a weighting factor for a cosine of a particular matching frequency omega. So we've got a cosine of a particular frequency omega and the amount A of that frequency. Then what we're doing in the synthesis, as touched on briefly earlier, is that we're summing over all of the various frequencies. So this summation is over frequencies omega. That means we're summing all of these various waveforms. Again, I'm only showing a few of them there, with the amounts A for each. So that's the amount A of a particular frequency omega. We're summing over all of those with a little normalization factor to reconstruct or to reform the original, to synthesize the original function f of t. So that's the synthesis for a simple, real-valued, even function. Okay, so that was an example of synthesis. Now let's look into how we begin to understand how to find the amount A of a frequency omega that is present in a given f of t. So how do we do Fourier analysis? Okay, so that's the question on the top right there. This is the synthesis expression here. Now, to understand how Fourier analysis works, we've got to understand, of course, that we're saying that the function f of t that we're trying to analyze into its constituent frequency components, we're saying up front that this is composed of all the various frequencies. Remember that grid of frequencies I was showing as an example earlier? Well, here I've just got 4 example frequencies: the 0 frequency, first, second, and third frequency, the number of waveforms fitting within a particular interval. And what we're trying to do is find the amount A of each one of those example frequencies that are present in f of t. How do we do it? Well, okay, it relies on the following property. Okay, this is just spelling out the question we're answering. How do we find the amount of each frequency omega? So how does it work? Well, all we do is say, if we want to find the amount A of frequency omega, then we create that waveform that we're trying to find. So imagine omega was corresponding to one waveform within a particular interval. So this would be, for example, cos of that particular frequency. It might be 1, for example. So we're trying to find A for frequency omega equals 1. So we do cosine omega equals 1 here. And all you do is multiply that by the signal that you're wanting to do the Fourier analysis on. So you take your original f of t, which could be that arbitrary waveform we've seen before, but of course we're saying it's made up of all of those components, then we multiply f of t by cos omega t, and so we get this. Then what we do, of course, when we're doing that multiplication, just to point out that therefore that cos omega is being multiplied by each and every frequency that is present in f of t. And this is the key to Fourier analysis, because when this function gets multiplied by itself, if indeed that frequency is present in f of t, when it meets itself in this collection of frequencies, we get this strictly positive cosine squared function, which when we integrate, when we take the area under the curve, will give a non-zero result. And in fact, it will give a result that's not just non-zero, it will give a result that is proportional to the amount of that frequency present in f of t. So what we've done then is we've taken cos of the particular frequency omega, because we're trying to find the amount of particular frequency omega present in f of t. So what we've done is multiplied, and then when we integrate, we get the actual, an amount proportional to that frequency that is present in f of t. And the reason this works, again, key thing to understanding here, is due to orthogonality of these frequency components. Because when this particular frequency omega meets any other frequency that's in f of t, it will, when multiplied, will give a function that's as much positive as it is negative, such that when you do this integral, you get 0. In other words, multiplying this by all of these frequencies will only give a finite result when it finds itself. All the others will look something like this: positive, negative, negative, positive. Integrate will give a 0 result. So I think I might have another example. There we go. So when this cos of omega t, this for example is omega is equal to 1, when this is multiplied by, say, this one here, the second frequency, where there are two waveforms within a particular interval, when you multiply this by this, you get positive, negative, positive, negative, negative, positive, negative, positive. It all adds up to net 0 when you integrate, and therefore we don't get any interference of any of the other frequency components when we're trying to find how much of this particular frequency is present in f of t. So that's the amount of particular frequency omega present in f of t. Okay, so we're now getting more of the picture, I think, about how Fourier analysis works. We take the input signal, we can find the amount of a particular frequency omega, and then we can, once we've found the amount of a particular frequency omega, we can use that amount of that frequency omega as a coefficient or a scaling factor for that very frequency component. And then we do the same, we add it all up for all of the various frequencies omega, so we sum over omega to re-find the original signal. And of course, the analysis stage, this A of omega, has been done for each and every omega, each and every frequency of interest. Right, and so that's the summary on the bottom left there of how we did the Fourier analysis. Take f of t, multiply it by the particular frequency you're trying to find the amount of, integrate, and that will give you something proportional to the amount of that frequency. Right, so far we've handled really real even functions. We've been mainly focusing on cosines, but as you're aware, functions are more general than that. We can't just assume that they're real and even functions. So here are the cosines, just an example collection that we saw earlier of various amplitudes and various frequencies. But in general, they could be differently shifted relative to the origin. So that would correspond, forgive the crude animation here, to a phase shift. So I'm just going to show that these waveforms could be differently positioned. Each frequency for each waveform could be differently located in the signal or functional image. So I'm showing that here by saying, well, okay, that cosine function could be shifted by what we call a phase shift, which is going to depend on the particular frequency. Okay, so let's see how we can begin to build in this more general model into our Fourier analysis and Fourier synthesis. So what we can do is exploit a trigonometric identity. So this is cos omega t minus the phase shift for a particular frequency omega. And we just recognize that that phase shift minus y, if I just simplify it here, can be expressed as, look what we've got, a cosine with no phase shift, a sine with no phase shift, where you can see that the phase shift of the cosine is taken care of just by the amplitude of a cosine with no phase shift and a corresponding amplitude of a sine with no phase shift. So you can get a phase shifted cosine by adding together a sine and a cosine with appropriate coefficients, and that will give you the net result of a shifted cosine. So this motivates then this kind of description, whereby to cover the case of shifted frequencies that are not necessarily nicely centered at the origin, all we need to do is do a Fourier analysis and synthesis for both cosine components and for sine components. And that will give us particular coefficients A, an amount A of frequency omega for the cosines, and an amount B of frequency omega for the sines, because those two combined will give us this nice general form where our frequency can be anywhere positioned according to where it actually is in our function or signal of interest. Okay, so that's what I've summarized here, then saying a cosine with any shift corresponds to a sum of non-shifted sines and cosines with their corresponding amplitudes. Right, so let's now do that then. Again, we've got our example sound waveform here. Previously, we'd shown it very simplified with just a few frequencies. I'm still only showing a few frequencies. Obviously, there are many more frequencies present with corresponding amounts, A of omega. But now we're also going to consider the sines as well, because by considering sines as well as cosines, we can now effectively get a cosine of any necessary shift according to what's in that signal. Right, so our analysis equation is what we saw before. Our synthesis equation for the real part is what we saw before. For the even part, the cosine functions, okay, is as we saw before. But now we've not only got the amount of frequency omega for the cosine, now we've also got to have an amount B of frequency omega for the sines as well. And so again, these combine to give just a phase shifted cosine. So therefore, to complete our synthesis, our Fourier synthesis expression, we now need not only to add up all the cosine frequencies, we also need to add up all of the sine frequencies as well. And likewise, our Fourier analysis, we need to not only analyze for the cosines, we need to analyze for the sines as well, the sine functions. And for the synthesis, we do need that normalizing constant there. Right, so we're getting there now, getting to the Fourier analysis and Fourier transform expressions. So here now we're saying that our Fourier synthesis is the cosines, various amounts A, and the sines with various amounts B. And then what we can do is use Euler's relation to substitute for cosine here. So I can point you to a video on Euler's equation, but if not, hopefully you know already that a cosine can be replaced by a sum of two exponentials divided by 2, and the exponentials have a positive and negative argument. These are complex exponentials. Likewise, the sine can be replaced by a difference, a subtraction of one complex exponential from another, again dividing by 2i here to get the sine component. And then if we now combine together both the coefficient A omega for the cosine and the coefficient B of omega for the sine, we can combine them together into a complex value, okay, a complex number f for a particular frequency omega. So this is the amount for the cosines, the amount for the sines combined in this particular form. Now you might be asking, hang on, why is there a minus in there? Well, we'll see that in the next slide as to why that is necessary. For the moment, just understand we've taken amplitudes of cosines A for a particular frequency omega, amplitude for sines B for particular frequency omega. Then once we've done that, we can now use this quite powerfully as complex coefficients, so complex values f for frequency omega, which can be used directly as coefficients for complex exponentials. So this Fourier synthesis is none other than the inverse Fourier transform. It's the inverse Fourier transform because this is not doing Fourier analysis. It's basically summing together the frequency components with corresponding coefficients, summing them all together to reconstruct or synthesize the original function of interest, here f of t. Right, so let's try and understand that Fourier analysis expression. So we've got f of omega, the complex amount f of frequency omega, given by that combination that we saw on the previous slide. Here are the Fourier analysis equations for the cosine and for the sine. So I'll refer you to what I've already described. To understand the cosine one, the sine is very similar. You just take f of t, multiply it by the sine of the particular frequency you're trying to find the amount b of. And so you multiply them and integrate, and that gives you b of omega for that particular sine. And so now let's look at what's happening then when we write this particular version for Fourier analysis. We're saying that the amount f of frequency omega is a complex value, and that complex value has a real part and an imaginary part. So we could write it in this form. Okay, so this is f of t with the cosine and f of t with the sine. And so what we've done here is take these two analysis expressions, plugged them into here to get this result here. So I hope that's clear. F of omega is a of omega minus ib of omega. A and b are here. If we substitute them in those integral equations, we get that expression. Okay, I still haven't explained where the minus is coming from. Hopefully that's going to become clear. And it will become clear here, I trust, which is that the corresponding overall Fourier analysis equation, in other words, the Fourier transform, is what we've just written. And all I've done is take this cos minus I sine and recognize that that is a complex exponential, e to the minus I omega t. Now, where does that minus come from? Well, remember we had the minus here, here, and here. Seemed a bit unusual. Well, that has resulted in the complex exponential having a minus here. And the reason that minus is important is because in the Fourier analysis, the Fourier transform, we're trying to find the amount f of e to the plus I omega t that is present in f of t. Now, to do that, we take f of t and we multiply it. Before, remember, we tried to find cosine and sine. We'd multiply it by the same cosine or sine. Well, to do the corresponding thing with complex exponentials, if we want to find the amount of e to the plus I omega t present in f of t, we've got to multiply it by e to the minus I omega t. The reason for that is exponential of a positive multiplied by exponential of the negative gives exponential of power 0, which is 1, which gives us our finite result after integration, and all the other cross terms, in other words, exponential of a different frequency with exponential of a different frequency here, when integrated, will give 0, just like we saw before with the example of the cosine. So that's why the Fourier transform works, relying on orthogonality of those exponential, complex exponential basis functions. So in summary then, we've got the Fourier analysis expression known as the Fourier transform, and then we've got the inverse Fourier transform, which we're calling Fourier synthesis. I hope that's been helpful in explaining to you the very basics of Fourier transforms, Fourier analysis, all the way through to the endpoint equations. Thank you very much for listening.